Good evening. This week we're going to start the study of forces. Up till now we've considered the motion of a body or particle in the abstract. This is known as kinematics, the study of motion, by which we mean the position of a particle as a function of time. But we haven't considered the cause of such motion, or the cause of changes in motion, which we refer to as acceleration. This week we're going to start the study of dynamics, which is the study of forces, the cause of that motion. In ancient times, Aristotle believed that a body that was put in motion would eventually come to rest. He observed that if you push something across the floor or through space, eventually its motion will stop. And he stated that it was necessary for an outside agent, a mover, to exert what he called an impetus on the body to compel it to deviate from its natural state of rest. This corresponds to what we commonly understand about, or what we can observe about the state of motion in the universe. It took until the 1700s, however, for Newton to come along and to realize that the natural state of a body is to continue whatever state of motion it's currently in. That is, if it's at rest, it will continue to be at rest. If it's traveling at some velocity, it will continue to travel in the same direction, the same velocity, indefinitely, unless an outside force acts to change its motion. He referred to this property of matter to continue in its current state, whether it's state of motion or state of rest, as inertia, which we now identify as the mass of a body. Newton's three laws, which basically summarize everything that we need to know about mechanics in this course, can be summarized as follows. 1. A body in motion tends to stay in motion, and a body at rest tends to stay at rest, unless a force acts to change its motion. By this we mean a body in motion tends to stay in uniform motion, traveling at constant velocity through space. Force is defined as mass times acceleration. The force on a body produces an acceleration, which is a change in the velocity of the body that's inversely proportional to the mass. Thus, if an equal force acts on two different bodies, it'll create a larger change in the state of motion of the body with a smaller mass. This is the principle we see behind the magnetic spectrometer. Here we have a beam of particles of different masses traveling through a magnetic field. The magnetic field exerts a force that's proportional to the mass as well as the charge of the body, although the effect of electric charge is something that will be considered in the second course in physics. Those particles that are lighter will have a tendency to be deflected more, that is, to experience a higher acceleration. Those that are heavier will experience less acceleration, and therefore will have less of a deflection. This principle could be used to separate the atoms of an element that have different atomic weights, in other words, separate different isotopes. Newton's third law, summarized commonly as every action has an equal and opposite reaction, or the force that a single particle transmits to a second particle is counterbalanced by an equal and opposite force of the second particle on the first. Nowadays we understand a lot about the different forces of nature. In ancient times, forces of nature were a fearsome thing. There was wind, there was water, sometimes the earth shook, and these were all things that were attributed to various supernatural agencies. In modern science, we have basically summarized all the different forces of nature to fall into one of four categories. The one that was known first in ancient times is gravity. Gravity, however, is the weakest of the four forces. The electromagnetic force began to be understood in the 1800s and was not understood fully until Maxwell in the late 1800s. We know that charged particles exert forces on each other. This is the electric force. We know that magnets exert forces on each other. These were eventually combined into what's known as the electromagnetic force. The mechanical force between two bodies is something that we will see again and again, such as a billiard ball colliding with another billiard ball, or a body sliding down an inclined plane. This is really the vestigial effect of the electromagnetic force, because the electrons that are attached to the atoms are all negatively charged, and like particles repel each other. This is why two solid bodies will repel each other when they're brought into contact. There are also two other forces, the weak and the strong forces, the nuclear forces, which the strong force is responsible for holding together the protons and neutrons inside a nucleus, and the weak force is responsible for transforming certain particles into others, such as neutrons transformed into protons, along with the ejection of a beta particle from the nucleus. So that's largely responsible for nuclear decay. Modern physical theories hold that in the early universe there was only one fundamental force. There was a combination of all four. And that as the energy in the universe decreased from the extremely high energies and temperatures near the Big Bang, the four fundamental forces became broken or separated from each other. Until now we have four forces that interact in different strengths and on different scales. The strong and the weak nuclear force being very short-range forces that are combined to the nucleus of an atom, and only the electromagnetic force and gravity act in the macroscopic universe that is the subject of this course. Newton's first law. Bodies have inertia, which we can now quantify as mass in units of kilograms. Bodies with inertia continue to stay in whatever their natural state of motion is unless an external force acts to change it. Consider a rocket ship moving through space. In space, there's essentially no gravity. There's some gravity from the sun perhaps, or the distant stars, but essentially it's in a state of zero gravity. And so objects that are released tend to continue in a straight line indefinitely. There's also no air resistance. So this represents the closest idealization of Newton's first law in action. If, however, the rocket turns on its motor, it will result in a force that can change its direction. Notice that even if the speed of the rocket doesn't change, if its direction changes, that results in acceleration, because acceleration is a vector and therefore corresponds to a force. This is also coincidentally an example of Newton's third law, because the force of the gas coming from the rocket's motor produces an equal and opposite force in the other direction that forces the rocket forward. Newton's second law, which we mathematically state as F equals ma, force equals mass times acceleration. This is a law that we're going to see over and over and over again in this course, and it's perhaps the most important equation that we're going to consider. Newton's third law, colloquially stated, every action has an equal and opposite reaction. Mathematically, we can state as the force of body 1 on body 2 is exactly counterbalanced by the reaction force of body 2 on body 1. An example shown here is that of an old Western gunslinger. A pistol, when it is fired, produces a tremendous force that ejects a projectile at high speed out the barrel. But everyone knows that it also results in a recoil effect. The larger the projectile, as in a shotgun shell, the more powerful the recoil will be. This is an example of Newton's third law, as is the rocket we just saw a minute ago. Another example is the skater. A skater on essentially frictionless ice will push off against the ice, which causes a force. The ice, on the other hand, exerts a reaction force, which is what propels the skater forward. We can think of this as a tug of war, essentially between two particles or two bodies, which are basically groups of particles. The force due to gravity is something that was studied extensively by Newton. For our purposes, gravity produces a constant acceleration at the Earth's surface. It varies somewhat with latitude and longitude, and it varies somewhat with altitude. As you go up a mountain, the force of gravity gradually becomes weaker. But essentially, since the Earth is roughly spherical, and since the elevation changes are fairly small, going up from a mountain up to the bottom down to the bottom of the sea, we treat the force of gravity, or the acceleration due to gravity, essentially as constant. This acceleration we call g, approximately 9.81 meters per second squared. The force due to gravity is, by Newton's second law, mg, which we call a body's weight. The mass, m, is measured in kilograms. The weight, mg, is measured in kilograms meter per second squared. 1 kilogram meter per second squared is known as a newton. Therefore, a body that has a mass of 1 kilogram will have a weight of 9.8 newtons. These terms are frequently used interchangeably, although they are not really. Now consider what happens when a ball is resting on a table. According to Newton's second law, there's a force, which is the weight of the particle downward. Therefore, it should be experiencing acceleration. But we know that a body left on a table will generally, if the table is flat, and there are no wind currents or other disruptive forces in the room, will stay where you put it. Why is this? Does this contradict Newton's second law? Well, this is really an indication of Newton's third law, where we have a reaction force which is exerted from the table onto the body. Were the table made of jello and the ball were a very massive object like a bowling ball, it would have a tendency to sink right through. Were it a sheet that stretched, the ball would tend to deform the sheet, but at some point it would stretch and it would resist any further deformation, and the ball would remain at rest at the bottom of the dimpled surface of the sheet. But for an extremely rigid table, almost no deformation is allowed before it can exert a force equal and opposite to the weight of the particle. Now, if the ball was sufficiently massive, say if it were the core of a neutron star, then any physical object on Earth, even the ground, would be unable to contain it, and it would be unable to exert a sufficiently powerful reaction force, and it would just sink on through to the center of the Earth. But for ordinary objects on the Earth's table, they have sufficient rigidity to generate a force equal and opposite to any force that is applied to it. Now, forces are vectors, and as vectors we can resolve them into components. We say that an object is in equilibrium if the net force, which is the sum of all forces acting on it, is zero. Picture here these two horses with a tug of war. One exerts a force F1 in one direction, one exerts a force F2 in the other direction. A rope, which is what connects the two horses together to the ribbon in the middle, is essentially an object that transmits a force along its entire length. This is true even if it goes around a corner or the rope changes direction. This is only true when the rope is taut. So although you can pull on a rope and exert an equal force at the opposite end of the rope, if you push on a rope, the rope goes slack and you won't transmit any force. If the two horses are pulling equally, then F1 plus F2, the vector sum, is equal to 0, and the ribbon in the middle will stay stationary. It's what we call an equilibrium. A two-dimensional example of this is illustrated by the force table, which is essentially a round table where a series of weights are suspended by ropes. We can measure the angle that the ropes make, and we can determine the force exerted on the rope, which is just the mass of each particle times the acceleration due to gravity. And in those cases, we can cause the vector sum. We do the vector sum by splitting each of the forces into components and then adding them component-wise. Again, when the sum of forces is equal to 0, the body is in a state of equilibrium. The concept of an inertial reference frame is important because Newton's laws only strictly hold in a reference frame that's inertial. What do we mean by inertial? Well, we can define a reference frame as being stationary relative to the Earth's surface. Now, the Earth's surface is not strictly stationary because, as we know, the Earth rotates on its axis. It revolves around the Sun, and the solar system and the entire galaxy, in fact, are moving through space. But for our purposes, this motion can essentially be ignored, and we can treat the Earth's surface as basically a stationary reference frame, meaning we can set up coordinate axes x, y, and z. A body that's moving relative to that will, from the point of view of an observer on the body, will see that the Earth seems to be moving relative to it. Part of one of the principles of physics is that of relativity, which is that the laws of physics should be the same regardless of one's reference frame. In other words, if I'm standing stationary and I see a train travel past me, by my point of view the train is moving. From the train's point of view, I'm moving. In reality, these are both considered valid viewpoints. So attached to an observer that's moving at some constant velocity v, we can define a new set of coordinate systems, x, y, and z prime. These define inertial reference frames if they differ as a function of time by some constant velocity times the time. If one is experiencing acceleration relative to the other, though, we say they are not inertial reference frames. Because in those frames, the relative acceleration will produce an apparent force in one of the reference frames that the other force does not experience. Here's an example of inertial and non-inertial frames. Inertial frames will have experienced the same forces because they have zero acceleration relative to each other by Newton's second law. Consider the frame of an observer standing on the ground, x, y, and z. We then have a bus traveling at constant speed. Assume that the road is completely flat and that the bus is traveling at exactly constant velocity down the road. Really an idealized situation. But to an observer on the bus, he has a reference frame x prime, y prime, and z prime. Now consider there's a table on the bus with a bowling ball on the table and experiences a mass, it has a mass and experiences a weight mg downward. Well, to an observer on the ground, the force on the ball downward would be exactly equal to its weight. To the observer on the bus, it would experience the same force. The speed of the ball would be different in the two reference frames, and it would differ by the relative speed between them. In other words, the speed of the bus. The two reference frames are related by this coordinate transformation, which we'd call a Galilean transformation. X prime is x plus vt, because the bus is traveling the x direction. Y prime is equal to y, and z prime is equal to z, because there is no component of velocity in those directions. The apparent velocity of the ball from an observer on the bus is equal to the velocity by the observer on the ground, except that it differs by the speed the relative speed between the two reference frames. If we differentiate this, however, because they're traveling at constant speed, we see the acceleration on the ball is the same in the two reference frames. So therefore, by Newton's second law, the force on the ball is the same in the two reference frames. Now consider what happens when the bus hits a bump. Now it experiences a sudden change of motion. In general, it may slow down, and it may also exhibit a sudden acceleration in the z direction. Well, we know what's going to happen. The ball is going to roll, meaning that it now experiences a force, which it didn't previously. Now consider what happens if we encounter not a bump, but if the bus begins to accelerate. We'll consider that it continues to move in the x direction. As the bus accelerates, we now suspend the bowling ball on a string. The string is going to deflect toward the back of the bus. That's because it now exhibits, in addition to its weight, it now exhibits a force due to the forward acceleration of the bus. Similarly, if the bus sharply decelerates, the bowling ball is going to deflect toward the front of the bus. Again, it accelerates a force. This in opposition to the direction of acceleration of the bus. Another example of a non-inertial reference frame would be where we have a reference frame that's rotating relative to another. Shown here, two axes, x and y, and another pair of axes, x prime and y prime. They differ by an angle theta. If the angle theta is changing constantly as a function of time, then we have a state of uniform rotation, which we'll consider in a few chapters. This results in a relative acceleration between the two reference frames. Remember, acceleration can be caused either by a change in motion in speed or in direction. This will also produce an apparent force in the frame that's rotating relative to our stationary frame. An example of this would be a school bus that goes around a corner very quickly, will go up on two wheels and could, if it's traveling fast enough, even turn over. Again, you'll see a deflection. In this case, it would be a deflection of the bowling ball away from the center of curvature of the motion. Now, the reaction forces on a body are exerted normal to the point of contact between the two. If two bodies touch like two bowling balls, the force will be exerted along the normal through the point of contact, which means it will act on a line that connects the two centers of the balls. Shown here is where we hit the 8-ball, unfortunately, into another billiard ball on the table. This produces a force that acts along their centers and will be the direction at which the acceleration of the second ball takes place. By Newton's third law, we know that this will also produce a reaction force, so the first ball will also be deflected. Let's see how this resolution of forces idea works on an inclined plane. In our first lab, we had the example of a body sliding down a ramp on an air table. An air table so that we could neglect the force of friction, which we'll consider in Chapter 6. And we said it experienced an acceleration equal to g times the sine of the angle. But we didn't specify y. Well, consider that a mass sliding down a ramp slides down because of the force of gravity, which we know is equal to mg, and it's in the minus y direction, straight toward the center of the Earth. We can split this force into components. We could split it into an x and y component, although in this case it'll be more convenient to split it into what we call a normal component and a tangential component. The normal component is in the direction that's at right angles to the ramp, and it's equal to mg cosine theta. There's also a tangential component at right angles, which is equal to mg sine theta. This is the force that acts down parallel to the surface of the ramp. Now, by Newton's third law, we know that a reaction force is produced when two bodies interact. In this case, the two bodies are the block and the ramp. The ramp, being a rigid body, will exert a force equal to Fn in the opposite direction. In other words, upward at an angle on the body that's on the ramp. Therefore, when these forces are added vectorially, they will sum equal to 0. And this is why the block cannot move either into or away from the surface of the ramp, but it always stays normal to the ramp. However, there's also this tangential component of force, which is equal to mg sine theta. Because bodies always exert forces on each other, normal to their surface and through the point of contact, there is no way that the ramp can counteract this tangential component of the force. Therefore, the tangential force is equal to the net force, or mg sine theta. By Newton's second law, acceleration is force divided by mass. Therefore, we see what we had already observed in the first lab in the course, which is the acceleration equals g sine theta. Only now we've proven it through applying the concept of revolution of forces in combination with Newton's second and third laws. So, how much of an incline would be necessary to simulate gravity on the moon? Well, gravity on the moon is approximately 1/6 that on the Earth's surface. It's equal to about 1.63 meters per second squared. Because the acceleration is equal to g sine theta, we could set up an equation: g on the Earth times sine theta equals a. And we're going to set a equal to g, the gravity on the moon. Well, rearranging terms, we see that sine theta has to be equal to 0.166, or theta is the inverse sine of this, which is 9.56 degrees. Therefore, if you set up an inclined plane at approximately 9.5 degrees, a body sliding up, down, or across will behave much as it would on the moon's surface. Billiards is a very popular game for demonstrating physics principles, and we see here an illustration of Newton's third law at work. We've already discussed that one ball will exert a force on the second that's equal and opposite to the force the second exerts on the first, or F12 equals minus F21, and that it acts through the point of contact and normal to the surface, which is a line that passes through the centers of both bowling balls. How can we use this to model the behavior of billiard balls on a table? Well, consider what happens if the second ball is stationary and we fire the first ball at it at some constant velocity. Before the collision, the net force is equal to 0 because the balls are not in contact. As soon as they are in contact, each one exerts an equal and opposite force on the other one at the point of contact. This changes the state of motion at both. There's an acceleration which is produced, which will impart a velocity to the second bowling ball, but it will also change the velocity, both the velocity and the direction of the first one. Using Newton's laws, we can precisely define, if we know the speed at which the balls are traveling, and we know the relative position at which the collision occurs, we could precisely determine their behavior after the collision. And we could do this no matter how many billiard balls are on the table or how many collisions take place. It becomes progressively more complicated, but in principle we could predict the entire behavior of a game of pool just from Newton's laws. In summary, Newton's three laws are the basis of all mechanics that we'll discuss in this course. The first law: bodies at rest tend to stay at rest. Bodies in motion tends to stay in motion. In other words, a body tends to continue in whatever state of motion it's currently in. We could summarize this as things have inertia, which is the property of a body to resist changes in its motion. The second law: force is mass times acceleration. More massive bodies are harder to stop. Massive isotopes are deflected less by a magnetic field than lighter isotopes. Freight trains are harder to stop than baseballs. And finally, third law, a reaction has an equal and opposite reaction. You can't pull yourself up by your boots. You can't push off against yourself. If you want to skate, you have to push off against the ice. Or, when you push on a wall, the wall pushes back. And remember, you can pull on a rope to transmit a uniform force, which we call the rope's tension along its length. But you can't push on a rope. This is going to be important in setting up all the future problems in this course, which is basically for the remainder of this course is applying these three laws to various situations. Bodies moving down inclined planes, bodies in a gravitational field, or bodies that are rotating on its axis. Now in Chapter 6, we're going to talk about a few special forces. The first of these that we're going to consider is friction. Remember that Aristotle believed that a body that was in motion would eventually come to rest, and this was a property of the natural state of the body. We now know by Newton's law of inertia, Newton's first law, that this is not the case. So what did Aristotle not understand? Well, friction is exerted by bodies on each other in reality. Often we'll ignore this in physics problems. We can ignore this when bodies are very smooth. There's very low, what we call the coefficient of friction. But in general, we observe friction, and we have to overcome friction. This is why cars burn gasoline. They have to continually burn fuel to continue to keep the tires rotating against the force of friction that's exerted by the road surface. No surface is completely smooth. Friction is caused by tiny surface imperfections where the force at a very small point can exert a very high pressure of one surface against the other on a microscopic level. Therefore, the smoother the surface, the more evenly this force is divided, and the less friction is going to take place. The rougher the surface, the more friction. Friction generates heat, which dissipates energy, and we'll see shortly that this results in dissipation of kinetic energy. This is the principle behind starting a fire. Using two sticks rubbed together, or a stick that comes to a point that can be used to generate a large amount of heat and start a fire in this example. Shown here also is the example of a surface, which is the surface of an apparently very smooth piece of metal, only shown with an electron microscope. We could see that all surfaces still have some residual amount of roughness, which causes friction. Now, what are the properties? We've already said that friction is a force. As a force, it's a vector, and therefore can be added to the other forces acting on the body to produce the net force and predict the future behavior of motion of the body. Force is always opposed to the direction of motion. And so if we have a block moving across a table at some velocity, it'll exert a frictional force that's opposed to that direction, as shown in this figure. Friction is different on a body at rest than it is on a body at motion. When a body is at rest, the tiny surface imperfections, which can generate a large amount of pressure of one body against another, can actually cause microscopic welds to develop. These welds have to be broken in order for the motion to begin. And so the force that's required to overcome that is known as the static friction. Once the body is in motion, these welds can no longer form, but there's still interactions due to the surface roughness. This is what we call kinetic friction. In generally, the force of static friction needed to get a body moving is greater than the kinetic friction needed to keep the body in motion. Now the amount of friction is proportional to the surface area of contact between the two. And this is the principle behind a wheel. A wheel will meet the ground in one point. Consider what happens when your tire, however, on your car begins to go flat. Now the tire deforms and it will meet the road surface in an increasingly large area. It causes the car to experience more friction, which requires you to put more fuel into a vehicle. This is a function of the surface area effect of friction. In this course, we're not really going to take that into account. We're simply going to define friction through what's known as a coefficient of friction. And then we're going to apply it to different problems. The coefficient of friction, however, is going to depend on the geometric contact point between the two bodies. Now the force of friction experimentally turns out to be proportional to the normal force on the body. Typically this will be the component of weight in the direction that it has against another surface. So a body sliding along a horizontal table is going to experience a lot more friction than a body that's basically sliding down a vertical wall. In the case of the inclined plane, the normal force is proportional to the weight times the cosine of the angle between them. So the frictional force will be proportional to that. The constant of proportionality is what we call the coefficient of friction. When the body first begins moving, this coefficient is the coefficient of static friction, mu sub s. After the body has been moving for a while, the coefficient is the coefficient of kinetic friction, mu sub k. Let's look at the free body diagram for a body sliding down a ramp. It experiences a net force of mg sine theta down the ramp, which causes it to slide. Opposed to this is a force of friction, which is proportional to the normal force, which is mg cosine theta. Therefore, the net force on the body is mg sine theta minus mu sub k, if the body is already moving, times mg cosine theta. Here we have a graph of a typical graph of the frictional force on a body when it begins to move from rest. Initially, the force increases until some maximum breaking point is achieved and the body starts moving. At that point, the frictional force has reached a maximum. Once the body starts moving, it settles down to a smaller force because, in general, the coefficient of kinetic friction is less than that of static friction. Shown here are some typical values. You'll see that kinetic friction is less than static friction in almost every case. Notice that it depends on the material of both bodies in contact. For materials such as Teflon, there is a very low coefficient of static friction. This is why Teflon is used in things such as bearings and machinery and so forth, because it produces very little friction, which causes small energy loss and also little heat generation. For rubber on asphalt, which is applicable to car tires on a road, kinetic friction on a dry road surface is typically 0.5 to 0.8. However, if the surface is wet, it can be dramatically less, maybe as much as half as much. This is what makes driving on a wet road surface so dangerous. Let's consider a sample problem to illustrate how this combination of forces works in real life. Consider a block that's being dragged across the ground at some uniform force, F. An example of this could be a cart that's pulled along the ground by a team of horses. This is being pulled at some angle, theta, and we want to know what is the angle that results in the maximum acceleration. Well, the first way to approach this is to draw a diagram that has all the forces acting on the body. there is the weight of the body, which is normal to the surface. In this case, since the surface itself is flat, this is just equal to the weight mg. There's the force of tension in the rope that's being used to pull it. We'll call that F. And opposed to the direction of motion, there is a frictional force, which it's, as I've said, it is in the opposite direction of the velocity, and it's proportional in magnitude to the normal force, or proportional to the weight. Okay, the component of the force in the upward direction is F sine theta. The weight downward is equal to mg. Because the car is never lifted off the ground entirely, nor does it sink into the ground, its movement relative to the ground's elevation is zero, and therefore the net force in the y direction must be equal to zero. So the normal force of the ground plus the component of the applied force, F sine theta, must exactly counterbalance the weight. The sum of these three forces must be equal to zero, or the normal force is mg minus the y component of the applied force, F sine theta. Now, in the x direction, the applied force has component F cosine theta. There's also a frictional force, which we said is proportional to the normal force. In this case, since the block is already moving, that's just equal to mu sub k times Fn. The sum of these is equal to the net force, and the net force is by Newton's second law, ma. So we have the equation F cosine theta minus mu sub k times the normal force is equal to ma. We substitute the normal force equal to mg minus F sine theta. And rearranging, this gives us this final expression for the acceleration. But how do we determine what angle results in the maximum acceleration? Well, this becomes a typical maximum and minimum problem. To find the angle that produces the maximum, we simply differentiate acceleration as a function of angle, dA d theta, and set that equal to 0. Rearranging, we see that theta equals the inverse tangent of mu sub k. Now let's consider a similar problem. Let's consider how we may determine the coefficient of static friction for a body on an inclined plane. The experiment is we place a block on an inclined plane that initially is inclined at an angle of 0, and we gradually increase the angle. And we increase the angle until the block begins to slide down the ramp. Well, again, we can split the force into components. We have a force, a normal force that's perpendicular to the surface of mg cosine theta, and we have a tangential force equal to mg sine theta. This is identical to the ramp problem we had before. The only exception is we now allow for the existence of a frictional force in the direction opposite to the tangential force. Again, the normal force is exactly counterbalanced by the reaction force of the ramp on the block, so those components add to 0. The tangential force, mg sine theta, is opposed by a frictional force which is proportional to mg cosine theta. Substituting these expressions together, we have the net force in the tangential direction is equal to the net force, as in the other ramp problem. This is equal to mg sine theta, the component of the force of gravity tangential to the ramp, minus mu s times mg cosine theta, where mg cosine theta is the normal force. In this example, because the block is originally not moving, we've used the coefficient of static friction instead of kinetic friction as in the previous version. The body begins to slide when the net force is no longer equal to 0. In other words, when the force of gravity down the ramp, mg sine theta, is too large for the force of static friction to overcome. So we set these equal to 0, we rearrange, And then again, we see a similar expression to the previous problem. We see the coefficient of static friction is equal to the inverse tangent of the angle. In this case, the angle at which the block begins to slide. This is a common experimental apparatus that is one of the ways in which we can measure coefficients of static friction. Another force that's very similar is air resistance. Friction is usually defined as the force between two solid bodies that are acting against each other. Air resistance, or more generally drag, is produced by the friction of a solid body in a fluid, either a gas, which we usually refer to as air resistance, or a liquid, which we could also refer to as drag. In this case, the force is experimentally found to be proportional to the square of the speed. So unlike the force of friction, it depends on the speed of the body. The faster the body is traveling through the air or through the liquid, the greater the drag force on it. If the body is traveling twice as fast, you'll experience 4 times the drag force. This constant of proportionality is what we refer to as the drag coefficient, and it's a function of the surface roughness and the geometry of the body. Some typical drag coefficients are shown here. For a human being falling through the air, the drag coefficient is typically on the order of 1 to 1.3. For a bird, which is a much more aerodynamic design, drag coefficient is about 0.4. A supersonic fighter has to travel much faster than a bird, so the drag coefficient is much smaller, so that it can travel at supersonic speeds without experiencing catastrophic heating. Consider a human being on a parachute who's in free fall. The net force is equal to the drag force minus mg, because like friction, it's opposed to the direction of motion. By Newton's second law, this is equal to ma. If we substitute the expression for the drag force, we end up with an equation that, for those of you who are familiar with differential equations, is a nonlinear second-order differential equation. Nonlinear because the velocity is squared. This makes these types of equations very difficult to solve analytically. They can be solved numerically on a computer, but it's very difficult to come up with an expression for the position or velocity as a function of time. But we can consider qualitatively what happens by looking at these graphs. Shown here is the graph for a body in free fall. As we saw in Chapter 2, for a body in gravitational free fall, when air resistance can be neglected, in other words in a vacuum, the speed increases linearly with the time. When air resistance is taken into account, because the drag force increases with the speed, this will cause an increasing deviation as we go to higher and higher speeds. It turns out that the speed actually reaches a maximum speed, which is achieved when the drag force is exactly equal and counterbalanced to the weight. Then the net force is equal to 0 and the body will continue to fall at a uniform speed after this point, in accordance with Newton's first law. How does this apply to projectile motion? When we fire a projectile in a vacuum, we know, as we saw in Chapter 4, that it follows a parabolic path. If, however, the projectile is fired in air, it will have a shorter range than it would otherwise. And as it continues to fall with greater speed, the effect of this will become more pronounced. This can be very difficult in coming up with firing solutions for artillery and factoring things such as wind speed and air resistance and so forth into effect is the hardest part of the problem. Now, in terms of the terminal velocity, we can find that by setting these two sides of the equation equal to 0. When the drag force is exactly equal and opposed to the weight, then the net force on the parachutist is 0, And this will occur when v sub t is equal to the square root of 2mg over the coefficient, the drag coefficient times the density times the cross-sectional area. This dependence on the area is important because this is largely the principle behind the parachute, which essentially sets up a large surface area which increases the force of drag and allows the parachutist to reach the terminal velocity sooner. Another example of a force is the centripetal force associated with uniform circular motion. We saw in a previous chapter that for a particle traveling in a circle at constant speed, it experiences an acceleration equal to v squared over r. Notice that it experiences an acceleration because velocity is a vector, and even if the speed does not change, the direction of the vector changes with time. By Newton's second law, this acceleration is equivalent to a force, which is mv squared over r. As a car goes around a curve, it experiences a force toward the center of curvature. That is the centripetal force. The occupants of the car feel a motion away from the center of curvature. In other words, they feel pushed outward. This is really a fictitious force that is often referred to as the centrifugal force. Technically speaking, we'll always refer to centripetal forces in this course. The centrifugal force outward is really a reaction force, and even though it feels like the occupants are being pushed outward, really what they experience is the force of the seats, the seat belts and so forth, constraining them to follow the motion of the car toward the center of curvature. Also a good example of the reactive forces in Newton's third law. Now, a car going around a curve experiences several forces. There's the friction of the roadway, exerting a force on the car's tires. The tires exert a force on the car's body mechanically. And when the tires are turned in a certain direction, they force a centripetal force toward the center of curvature. And there's also a reaction force, which is why the occupants continue to stay in the car and not fly off at a tangent, which is what they would do, perhaps, if they were traveling fast enough and not wearing their seatbelts. Finally, in the study of friction, let's consider a couple of sample problems. Let's consider first a car on a flat circular track. Drawing the free body diagram, the car experiences a force downward due to its weight, and an equal and opposite normal force upward, force of reaction. It also exhibits a force toward the center of curvature, which is what causes it to go in a circular motion. Now the car tires are rolling on the surface, so even though they are in motion relative to the ground, it's a rolling motion. And when we're dealing with rolling motion and not sliding, we use the coefficient of static friction, mu sub s. If the car was sliding, as in a skid, we'd use the kinetic friction. This friction is what produces the centripetal force. So therefore, the force of friction, which is mu s times the normal force, is equal to the centripetal force. Mu s times F of n equals mu v squared over r. There are also lift forces, which may be due to the force of aerodynamics on the body. For a car, these are generally not very serious, although for a race car, a certain amount of lift can be designed to help it corner better. Certainly on an airplane, the lift forces are dominant and what caused the airplane to lift off from the runway. But in this case, let's assume we only have the two forces, which are the weight and the centripetal force toward the center. Substituting the normal force into this expression, we have mu s times mg equals mv squared over r, or, rearranging, mu s times g equals v squared over r. We can use this to find the maximum safe speed g. This is the maximum speed that a car can travel safely and the frictional force will still be sufficient to compel it to move in a circle. If the roadway is very icy, the coefficient of friction will be reduced and the car will not be able to take the curve safely. This is a typical problem on our highways. How is this solved? Well, one way this is solved is that road engineers will bank the surface, which means they'll put an incline into the road surface going around a curve. How does this help make the road safer? Well, consider that the car moving around a curve will have a free body diagram that's very similar to that of a body sliding down a ramp. There's a normal force and there's a tangential force. In this case, it is the tangential force of the body sliding down the ramp that produces the centripetal motion. So in this case, Fn sine theta equals mv squared over r. In this particular problem, we made the assumption that friction can be neglected, because what we're trying to do is we're trying to derive what is the bank angle that we need to design for this road without taking the friction into account. Similarly, there's a normal force, Fn cosine theta, but that's exactly counterbalanced by the weight, mg. So we could say Fn cosine theta equals mg. If we take the ratio of these expressions, then Fn, the normal force, will cancel out, and we're left with just the tangent of theta and an expression where the tangent of theta equals v squared over rg. Therefore, if the road is banked at an angle theta, which is equal to the inverse tangent of v squared over rg, or greater, then even on a road surface where the coefficient of friction is essentially zero, which could occur on a very icy road, this angle will be sufficient to keep the car safely on the track, even when friction can be ignored. Of course, as with most things in engineering, there's a large margin of safety built in, such that in general for a dry surface, this produces a large margin of safety. So you could actually corner it at a much higher speed and still remain on the road surface. However, this is essentially the physics behind road engineering, where we're designing the bank angles of ramps, we're assigning the maximum safe speed on a ramp, and so forth. For cases like the Autobahn in Germany, would be designed for even handling higher speeds.